Today we start with one of the video recording of one of the applied mathematics that we have. We call it calculus, and which is being taught in Math 102. Calculus is divided into two main sections. We have what we call the differential calculus and the integral calculus. The differential calculus is popularly called differentiation, and the integral calculus is called the integration. The differential calculus is to find the rate of change of a function. That is how a function changes with respect to time by considering time. That is differentiation. Geometrically, if you are to represent this statement using what we call diagram, I can give you this. I can say, right from our primary school, right from our secondary school, we were told that when we have a function, a Cartesian plane, representing y and x, this is a Cartesian plane, and in this Cartesian plane I can have a straight line curve, and this straight line curve is always represented by y equals to ms plus c. In this straight line curve we can have 2 points selected, which is x1 and x2. Also corresponding to it, we have y1 and y2. There can be change in s here, there can be change in y here. Then we are expected to find the slope of this graph, and which is represented with m most of the time. And this slope is represented with change in y with respect to change in x. That is what I've just given to you as a definition of differentiation now. I said differentiation, it is the rate of change of a function with respect to time. Now, rate of change of a particular function is change in y with respect to change in x. So this gradient, this slope is otherwise called gradient. So when you say gradient, it is change in y with respect to change in x from this graph we have just drawn above. That is the geometric representation of differentiation. So differentiation is the same thing, or it is synonymous to the word gradient. Moving on, we can also say in practical application, differentiation, physically speaking, it is when you are looking for the speed, it is finding the speed of an object with respect, finding the speed of an object if you are given its position as a function of time. The speed of an object, how fast an object is moving. The speed is what? Distance over time. That is also talking about what we call differentiation, or what we call difference, or what we call gradient. Moving on. We can also be asked to find the gradient or the slope of a curve. This is a straight line graph. We can be given any form of curve, which can be parabola or any other type of curve that you can have. This curve, if you are finding the slope of this type of curve, let me represent this curve like this. We are still dealing with what? A Cartesian plane. And in this Cartesian plane, we know that we have the y-axis and we have the what? The x-axis. Then if you are asked to find the slope of a curve when you are given a parabola, let's assume I have something like this. This is not a straight line curve. If I'm looking for the straight line curve, I can easily choose any two convenient points and add the slope. But in this case, I will not be able to choose any point conveniently because the line changes immediately, continuously. So what we do to find the slope at this particular curve is to draw a line. And this line that we have drawn, which must be a straight line, this line that we have drawn, which must be a straight line, is called the tangent to this curve. It's called the tangent to this curve. Now, this is a graph which is y, and it is a function of x. We are going to explain the concept of function later. This is a straight line drawn to this curve. It is only this straight line that represents the straight line that we have here. We can only get the slope of this curve from this tangent drawn to the curve. So in this case, we have to look for the gradient at the point where the tangent meets the curve. The tangent meets the curve, let's call it P here, and this is a point which is very close to the P, we call it Q. We can also have the same illustration here, we have x1, we have another one, we have x2. Don't forget that we can have y1, then we can have, this one is what? From here to here, we can have it to be change in y here, then we can have y2 here. Just as each of these points can represent s1, y2, s2, y2, x1, y1. Each of these points, they have their representation there. And in this point, we have change in x here. Then in this point, we have change in s here. Then we have change in y here. Here, we use this delta x, delta y. This one is capital delta. It's just a Greek representation of increment or change. It means nothing. This small delta also represents increments or change. It has nothing to do with our calculation. It's just rate of change or something. It's just increment or change with respect to something. So in that case, we have change in s and we have change in y. We have change in s with respect to change in y. So in that case, we can also represent the slope of this curve. The slope of this curve will be the slope at the point where the tangent touches the curve. That means our slope will also be equal to our gradient. And our gradient is change in y. According to the first representation we have here, you can just say change in y with respect to change in x. Now looking at this very well, this is my s1 and this is my s2. My s2 is going to be s plus change in x. This point, this is x1, or let me just call it x. With this change in s, this is the second point. The same thing is applicable here for my y2. I won't have y2 here, but I will have y plus change in y. So there is something that we have to note here. S plus change in s is the second point instead of calling it s2. Y plus change in y is the second point instead of calling it y2. The addition of these two will give us this. So there is something that you have to equate here. This one is going to lead us to a very important concept, or the first concept, or the first formula to evaluate gradient. We can say since we know that y is a function of x, when we call a function, a variable, a function of another variable, this particular variable that we call y depends on x. That is, for you to get the output in the y-axis here, which is the vertical axis, you must first evaluate the value of x-axis. That is, the value that x has will determine the value of y. That means if y is 1, then if x is 1, then you determine that y from x. What I'm saying is this: if I have y as a relation to be what, 2x, if I have twice of s making up y, if I are giving s ranges between 1, 2, 3, inserting x in turn, then when you put s to be 1, y will be 2. When you put s to be 2, y will be 4, and so on and so forth. This depends on the value of x. That's why we say this one is a function of this. The function that this one performs determines this. So y is called the what? Dependent variable, because it's dependent variable, because it depends on x, and this x does not depend on anything. So we call it what? Independent variable. You have to get these two things right when you are dealing with differentiation. So I'm saying that this is y, which is a function of x. Look at these 2 points. We are going to equate these 2 points as s, and this is s2. Yes, it's equivalent to s2. This is also y2. Yes, this is equivalent to what? y2. So we can say y2 should definitely be a function of what? s2. So we can have y plus change in y, which is equivalent to y2, equals to s plus change in x. So this is going to lead us to a very important concept in differentiation, which we call the first principle. See the way we are going to get that now. So making change in y the subject here, change in y, and y goes to the other side, s plus change in x minus y. Then change in y is equals to s plus change in x minus my y has been represented as f of s, substituting that f of x. So this is f of x. So we can make this one to a function of x, f of s plus change in x minus f of x. So this is change in y. So I've gotten change in y to be f in the bracket f of x plus change in s minus f of x. This takes us to gradient. Now talking about gradient, we know that gradient is equals to change in y all over change in x. Applying that here, we have change in y to be equals to f of s plus change in x minus f of x all over change in x. All over change in x. These two notations represent the increment in s here and the increment in y here, which is the second point of x, second point of y. And this increment we have in y here, that is the distance between this place and this place, is what they are talking about. That is the increment in y. That is, this is y1, of course. Then from here to here, we have increment in y. This increment in y starts decreasing as this s increases towards. When I decide to move this s closer, let me say this s2 now is being moved closer to this x. There is no increment in s now. So I try to move this second point of s2 closer here, closer here. Then this tangent line that I've drawn will get closer. This open space will get closer up here. That I'm explaining can be represented mathematically by saying, by limiting. This represents limit. We call it limit. That is, I'm reducing something. Limit the change that I have in y. This one that I'm talking about. Getting it closer up. There is a change there, which is this small space. Getting it closer up with respect to the change that I have in what? In s. It's the same thing. Limit the change that I have in x as my change in x gets to 0. That is, there is nothing like change in s here now. It gets closer, get closer, get closer until it gets back to the first point. Then what happens is that f of s plus change in x minus f of x all over change in x. Then what happens to these two? Then we have total derivative, which is the y, the x, and this one still remains lim as change in s goes to 0, f of s plus change in x minus f of x all over change in x. Then this gives us what we call the first principle for differentiation. First principle for differentiation. For differentiation,